Good morning, and today's topic is, well, it says bad tech, so we're going to look at some negative consequences, and we're going to try to connect them to our AI interventions as well a little bit. So, basically, the idea is, with AI for nature and environment, we're trying to do good things here. It's important to consider what could go wrong, and we want to look at the sort of whole system perspective. So here we're going to be looking at some quite general topics related to implementation and things like this. Machine learning is kind of the core of what we want to do, but a lot of the examples will be about the whole system. So we've done a little bit of the possible downsides already, but we are going to start with bad side effects. So this is something that, well, it'll be very obvious once we start going into it, but then, so the side effects could be bad, but then actually more of the time we'll have a look at when, forget the side effects, just imagine the solution itself and whether it's going to work. So we'll look at different factors that might limit the impact of these things. And this is not entirely a negative lecture. It's partly about how to avoid bad things, but there are some good things in here as well. So we're going to look at which types of technology make sense to be applied globally, and nature-based solutions will be the sort of closing topic for this morning. So we start with side effects. Even if our intervention has a positive effect, it can also have some negative effects, and we've already covered some of these. So we've got, let me set this. We've done quite a bit about carbon dioxide emissions or climate change impact. We've also talked about e-waste a little bit. That was in the devices lecture there. It should say devices. And we've also talked a little bit about wildlife disturbance. So this was in the biologging lecture where we're actually attaching things to animals. So, of course, in each of these situations, we want to weigh up the costs versus the benefits. And the side effects are not always obvious. So, as we saw in the electricity lecture, there's the direct electricity use of your computer doing the calculation, but there are some always indirect effects as well, such as the power used to cool the server room where your computation is running. So the side effects are not always obvious, and we can't always take account of everything in advance, but we can try. So wildlife disturbance. If we tag animals or catch them, then this can alter behavior. Now, this isn't only about tagging, so this isn't only about attaching devices to animals. Quite a common way to study many animals in the wild is to just temporarily trap them so that you can, for example, identify them and decide whether they're this individual or that individual. So with birds, for example, you might catch them in a sort of a mist net, like a net stretched between two trees. And then what they do is put a tag on just a band on the bird to give it an ID, and that helps them to monitor the population. But it has been found that birds that have this can sort of learn to then avoid basically humans, and so they don't get caught in the mist nets in future, and that means that if you're trying to estimate the populations, then you've actually introduced a little bit of bias there, because the birds are behaving slightly differently. So we also spent a lot of time on static devices like camera traps or acoustic recorders, right? And so those devices just sitting there, much less disturbance. Very often, the animals are really, really ignoring these things. But of course, there's not zero disturbance. Part of this depends on how often you need to visit the site to change the batteries to fetch the SD cards, right? So one of the things we talked about with bandwidth was it can be surprisingly effective to go and collect the SD cards rather than to set up some kind of 5G connection or something like this. But then, of course, we've got a side effect, because if you're going to the site every 3 weeks, then maybe that disturbs the animals. Maybe the animals are going to avoid the exact site that you're monitoring. And smartphone citizen science, of course, that basically relies on someone being there for every detection. So that has more impact in terms of disturbance than the static devices. And remote sensing, almost the definition of remote sensing is that there's no disturbance, because that's basically where the idea comes from. We're going to find ways to sense the situation without having to visit, without having to intervene. We focused on satellites, planes, and drones. In fact, the lack of disturbance is not entirely true because, well, one of the questions is, if you're flying a drone over a flock of birds, they're probably going to notice, right? And actually, one of the things that's slightly worrying is that the behavior of a drone is kind of similar to the behavior of a predator. If you have a bird that's, what's it called in Dutch, a roofvogel, a bird of prey, then, okay, they're going to be flying somewhere near the flock. Maybe they'll follow the flock around, and this is exactly what probably your drone is going to be doing as well. So there is a concern that if you're using drones, then you might have to have particular limits, like, okay, make sure it's a very long way away, or whatever kind of precautions you can take. But it does mean that remote sensing with drones or planes might not actually be completely disturbance-free. So this work that I talked about, they actually investigated this. So this was in Scotland. They took drones up to wetlands and they sort of tried different distances from different species of birds. And so, yeah, flying the drones at 30 meters height, which is pretty typical, and they find that, okay, some flocks of birds do get disturbed and some birds don't. So in most wildlife studies, the answer is usually it changes per species. All these different types of animals have different reactions. Flushed here means that the birds flew away as a flock. And so for fields and coastal sites, they found that there was quite a big effect of this. On the other hand, maybe the birds can sometimes get their own back. I just love this photo. That's why I've included this. So this came from a police exercise in Katwijk where they're actually training roofvogels to get the drones. Now, this isn't wildlife fighting back. This is the police coming up with a nature-based solution, right? But I think it's great. Anyway, if you want to get into training birds, this is maybe a new career opportunity. So that's disturbance. So now disturbance here is a bad side effect. Now another bad side effect is we could actually be, by our surveying, we could be giving information to bad actors. So that means people who don't have the same intentions as us. If we have public information about species location, so we've talked about GBIF, this was something I introduced in lecture 1, where we have this global, free, open database of all of the animal observations. Now, part of the problem there is that if you are a trophy hunter, poaching, stealing eggs, maybe this isn't useful information for you as well, right? And it is, and it's a concern. So with pretty much all wildlife monitoring, this comes up as a concern, and this partly is solved by hiding some of the details. So for all of these systems, when you have a species that is identified as a very high risk of extinction or something like this, then the actual details are often hidden. So if you go to GBIF and you search for certain types of animals, you won't find the information because it's protected and you have to apply to have access to that information. And that certainly applies to Sino Canto, the audio database as well, and we did that as well for the Citizen Science phone app that we produced, delaying the release of information. So you don't have to hide everything. If you delay the information by 1 year, then it's not going to be useful for people who are hunting because it just gives them the same information as general, a handbook of animals. But this can happen in lots of different ways. So this is an example for wildlife. The same can happen for carbon emissions, all kinds of things. If we're making a lot of public information available, it's worth thinking about what someone would do with that information if they didn't want to go along with the restrictions that maybe we sometimes have to have for nature. So that's side effects, but now let's actually focus on the main effect. Does the tech work as well as expected? And so this is kind of going to be one of the main things that we'll talk about this morning. When we design a machine learning workflow, as you know very well, we have 3 stages. We have training, validation, and testing. Part of the idea of having this test data set is we are using it to estimate the performance of the system out there in the wild. Right? So it's not just for getting a score. It's not just for saying one thing's better than another. It's specifically for trying to estimate how well the system will perform when you deploy it. But usually it's not really like that. You test it, and then you take it out in the wild, and then you really test it. And what would be a reason for this? The performance might be different when you actually take it there for real rather than you have in your test set. Just give me a reason or two.
Bias in the data set?
Bias, yes. Okay, so the bias could come from the way the data set was collected, for example. Yeah.
Also noise, so different lighting.
Different lighting. So different lighting in the test set as maybe the actual deployment. Yeah. So these are 2 different ways in which, essentially, the data in the test set are not representative of the data out there in the wild. And it's as simple as that. It's pretty rare that your test set is going to be genuinely representative of the situation out there in the wild. So if I develop a system and I claim that the performance is 95% in my tests, I'm really going to have to come to terms with the fact that if the performance is 80% out there in the wild or less, is it still going to be worth deploying? Is it still going to have the effect that we want? Yes, and here's the form, is in text form. So it's always limited to the data you are able to collect, and that's always one of the big bottlenecks in applying machine learning to almost any topic, but certainly to this one. We've just talked about exactly this, the sort of lighting that you might get, the sort of capture conditions, and certainly weather as well, and usage. Here I mean that people might use your system in a different way than you expect. If you collect data that is equally spread across the country and then people use it only on the coast, then that pattern of behavior might lead to different performance than you expected. Okay, so that's that. Now we want to get slightly more theoretical or holistic about this. There are a couple of systemic limitations that are actually mainly discussed in the economics literature, but this it's a nice way to sort of really consolidate the idea that things might not work the way you expect. And the first one is the rebound effect. Do we know this at all? I don't know if this is. I don't know if you've studied any of this kind of topic. All right, so it's very common that systems adjust. So if we make an intervention in the wildlife out there, it's very common that the overall system adjusts, and that might be something physical, or it might be people's behavior adjusts to the presence of your new technology. And that sort of adjustment, that sort of compensation, can often lead to reduced overall benefit. If I wanted to introduce something to make life more efficient, then people might just do more work as a compensation. And that has been observed in a lot of situations. And this can go kind of extreme, which is in the second thing, which is called the Jevons paradox, which is kind of taking this to its extreme, which is if the adjustment is such that we are making a particular system more efficient, then people use more because it appears cheaper. And overall, our intervention could make the resource usage worse rather than better. So let's look at a couple examples of this. Firstly, the Jevons paradox was invented by this fella, Jevons, in 1865. And this is one of these occasions when it's kind of amazing how far ago in the past people were thinking about these things, because this is someone who was thinking about whether the British Empire would run out of coal. And so he written this document, The Coal Question, about the progress of the nation. And in it, he suggested that because of the invention of the steam engine, so now the steam engine is a much more efficient technology than what went before, and so it makes better use of the available coal. But he suggested that that fact would mean that people use more and more, and they convert basically the whole economy to using this fabulous steam engine. As a result, the country uses more coal quicker than it would have done. So this is him in 1865, and it's obviously a slightly climate-related topic that he even started with. You know, in the end, the Britain didn't run out of coal just yet, but different things happened than he expected. But still, there it is. And let's take a more modern example. These are some fictional numbers. I just want to really make sure we can put numbers on it. If we take an old-fashioned light bulb that might be 60 watts, consumes 60 watts of power, then we replace it with 6-watt LED bulb. So we've now got a sort of 10-fold improvement in power usage. If, for some reason, my power supply has different efficiencies when it's running at different levels, and this can happen, but this example is fictional, just to put some numbers on it. But if the power supply compensates, so this is exactly the rebound effect that I've mentioned, right? If one thing becomes more efficient, then the system sometimes adjusts in some of these ways. If the system is actually less efficient when it's supplying a small load, then actually the overall reduction, the losses at the power supply need to compensate so that we get 6 watts at the output. So an 80% efficient power supply, we need to supply 7.5 watts. And so the improvement is still an improvement, but it's not tenfold. So that's a very physical example of the rebound effect. Perhaps more commonly, it's a behavioral thing. Maybe I've got 60-watt light bulb and I replace it with a 6-watt light bulb. Maybe my behavior changes and I become less concerned about turning the lights off. And there we have, I'm using more time, so in the end I'm using still less power, but not as much less power as expected. So this kind of thing can be physical or it can be behavioral. It's the overall system including the objects and the people, of course. And then if I take that to the Jevons paradox extreme, if I get enthusiastic about these super efficient light bulbs and I buy 12 of them, and I run those instead of one 60-watt light bulb, then okay, now we've got 72-watt draw on the system, and that's actually using more power because the system has become more efficient. And that might seem a little bit extreme, but LEDs are used in a lot of places now that they weren't used before, right? They're really spread. You know, it used to be that we would just have one light bulb in the middle of a room, and now we don't. We have something maybe approximating these things. I don't think this is happening a lot. We don't get Jevons paradox in a lot of lighting, but I'm using this example because we can get really simple numbers on the light bulbs. All right, so what we want to do a little bit later is try and apply these ideas to some of the machine learning-based interventions that we've talked about. Now on to factors limiting impact. This works as an example of the rebound effect. If I'm providing public information, okay, now this is more about information for bad actors again. If I'm providing public information about monitoring, for example, if we publish our observations, then that tells everyone where people are monitoring. So now if I'm a hunter or something, an illegal hunter, then I might use this information to avoid capture. So unlike what I said before, this works as an example of the rebound effect, because now if we are creating a public monitoring system and the thing that is being monitored avoids being monitored, then this feedback loop reduces the effect of what we wanted to do. Essentially, we fail at the monitoring task to some extent. So this is the rebound effect, and this could happen and this can happen. So when we design systems, we have to be careful about who has access to the information sometimes. Now, in wildlife and climate, we're in a fairly nice position that we're trying to do some good things, and most people want those good things to happen. But of course, there are various organizations or people that sort of disagree with how things should be done. There are plenty of reasons to do this. I won't go on with that. Yes, this is another side of behavior, which is about nudges. Let me see where I'm going with this. Nudge theory. Have you heard of this? Nudge theory? Have you seen this sign? 80% of hotel guests reuse their towels. This seems to be everywhere in hotels for the past 10, 20 years, as far as I've seen. The idea is that if you make a small intervention on people's behavior, we're not banning people from using towels, we're not taxing them for using towels, but simply giving them some information. 80% of hotel guests reuse the towels. Then this doesn't put a strong cost on people. They can reuse their towels. They cannot reuse the towels. They're getting very little cost either way. But this very small nudge, this small piece of information, is predictably going to change their behavior. So that means that quite a large number of people, doesn't have to be everyone, but quite a large number of people with this kind of information will say, okay, I'm going to go along with what I think majority behavior is, and I'm going to reuse the towels. So the important point here with nudge theory is that you're making a small intervention and having a larger impact than the force you've put in. And the question is, will that work? So in this example, I'm going to have to tell you what that says down there. This example is nudge theory in action on climate and energy. It's about your energy use in your home and the cost that it might have. So there's an idea that if I have an aggregate energy bill which says I'm using 7.5 kilowatt hours per day, then, maybe I'm cost conscious, maybe I'm environment conscious. Either way, I want to reduce the bill or at least be in control of it. The idea is that if we give you an itemized energy bill, then we're going to be able to sort of reduce that. I'm going to be able to say, maybe I'm not going to use the washer dryer so much, or maybe I'm going to use it when the electricity is cheap. Various things like this, right? This is a pretty common idea that you can give people feedback like this. And the nudge theory idea here is we're not putting any taxes on, we're not putting any restrictions on, but people will adapt given this information. What it says down here is visualize energy use. Users can make better choices. And so here, in a little bit more detail, so now these slides about energy disaggregation, these come from some research by a researcher called Jack Kelly in the UK. This was his PhD project. And so energy disaggregation is the idea of using machine learning to enable this kind of thing. It's very common in most people's homes that you don't get the itemized bill. What you get instead is what you see on the left, which is just some kind of time series of how much energy is being used at any one moment. And maybe the idea is that that's not good enough. But this time series, we can think of it as a machine learning problem to kind of infer what's turned on when. And the way that works is because there are different patterns in the time series, right? So we can see at some point there's like a sudden spike, at some point there are a lot of different spikes, and then at some points there is just this base load increase and decrease. And these patterns in the time series should be something that we can identify with machine learning, given enough data. And then we can do a disaggregation, as you see on the right-hand side. Part of the reason that I'm showing you this example, and we don't have a lab on it, but I'm just showing you this example, is that what this researcher, Jack Kelly, did was develop some of these techniques and piloted them, but then reviewed the work that had been done on these things. So this was 12 different studies where they actually take this disaggregation approach, try it with people, with their own homes, with their own electricity bills. And the summary of the research was that it can reduce energy use by about 4.5%. People are taking smarter choices. The bad news is that if you just give them this basic graph, that already reduces their energy use by 3%. So it's kind of like simply being conscious of the basic fact of energy use is the biggest effect here. And just because of the relative scale of the studies, is actually, you can't be sure that this 4.5% and this 3%, if they're really different effects. So in this summary, he said that the difference might not even exist. More research needed, but the difference might actually be zero. So when you're faced with this kind of situation, you've got two choices. We can either make this better. Maybe there's a better way to visualize the information for people. Maybe a nudge isn't enough and you want to bring in a stronger intervention. Or maybe you just try something else. Another interesting example about behavior. Now this is again using machine learning in kind of unusual ways to nudge behavior. This paper from 2021, they're using generative AI here, and it's called Using Artificial Intelligence to Visualize the Impacts of Climate Change. So they are taking, this is a real photo in the top here, and what they're actually doing is developing a system which casts forward 30 years or 50 years or 100 years, and you can see that we have a relatively, what shall I say, stereotypical picture of what might happen under climate change in certain parts of the world. Now, since 2021, generative AI has kind of really come along a lot, and so you could just ask any old system to add water to a scene. It's not as simple-minded as that. It actually tries to use some models about what changes will happen in which timescales. But an important part for them developing this, they claim that part of the reason that our concern about climate change doesn't turn into action is that, as it says there, it is difficult to mentally simulate the effects. So the idea is that by making it a bit more visible, just like with the electricity meters, by making it a bit more visible, we are making more realistic the possible outcomes, let's say. And so what they actually did with this, they made a website where you can put in your own location and it'll find like a Google Street View image and then sort of transform the Google Street View image. I want to ask at this point, what do you think about this? Do you think this would have an effect?
I think, most people just don't really care still. So.
Yeah, I think that's fair. Anyone got a different suggestion? Yeah.
I can see your house underwater. It's like better visualization of the trend, and then you get more of it. Because you're like, oh, this is my house, and it can get submerged, and I
Yeah. So certainly part of their motivation is that, if it's your house in the picture, then that can have a much bigger impact than generic projections. And that's certainly part of their argument. I find it a little bit of a strange claim that this is a good idea because, one thing from my point of view is that there are a lot of places where your house won't be underwater. So if they're doing it genuinely, then you'll visualize it 50 years from now. It'll look the same, kind of. Maybe the grass will be less green. I don't know. Another thing that concerns me about this is that this is quite literally fake news. We're generating images and trying to scare people with images, and I'd be quite concerned that if we take this kind of approach, then it's very easy for people to say this is fake news, because it is literally fake news. It's, yeah. The general impact I find kind of, but I think things are changing, and now that we have generative images everywhere, I don't know, maybe people's relationship with these generative images is different than it would be 5 years ago. So I think, yeah, to be seen, to be seen. So, thank you. So I've put a lot of negative things here. All is not lost, right? So it's not that nudges don't work. They can be effective. But we have to be careful with assumptions about how people respond to technology in use. And of course, a good way to handle that is to have pilot studies where you're actually deploying the technology that you want to deploy widely. So, we've considered a lot of different things that might limit impact or have side effects. I would like to see if we can connect this to some of the stuff that we've seen in the previous lectures. The next thing we want to consider is about whether some of our solutions are going to work the world over. And so I think it's fair to say that many solutions, especially tech-based solutions, things that might involve machine learning, might be rich world-only solutions. Why would that be? Yep. So computationally expensive is the main thing, yeah? Yeah, something else?
Also they're possibly maybe expensive as monetary value.
Yeah. So the devices or other things, yeah, absolutely. Does anyone have something else to add? Why it might not work in poorer countries?
Technology also. Technology limits. So technology is still probably in poor countries, technology is still not developed as well as in rich poor countries.
Yeah. So one way I would put that would be that there might be a sort of infrastructure that is needed, which might be a tech infrastructure that isn't there. Thank you. Do you have something? Thank you. Yes, that's one that I was hoping for. Yeah, absolutely. It's a good one. So the data that we've trained our algorithms on might be from the rich countries only, and then we lead to the problem that I referred to about generalization. So why would the data be from the rich world only? Yeah, absolutely. So one of the things that happens plenty in socially positive actions in richer countries is that we rely on, for example, a lot of volunteer effort, and then in poorer countries that volunteer effort might not be available because maybe they have bigger problems to worry about, at least for the time being. So yes, person time, that could be volunteers or even paid person time, might not be available. And that's one reason that the data might not be available. So here's my list. Cost of sensing devices and compute power, that's what we started with, that's good. And actually this is one aspect of the infrastructure. So smartphones, good broadband internet and so on. In many poorer countries, people do have phones or smartphones, but that doesn't necessarily mean that they've got credit. It doesn't necessarily mean that they've got data connections. So actually having a strongly connected network is part of the limitation in a lot of situations. We just talked about the fact that citizen science assumes that you have a lot of volunteers with spare time. Now, that can bias data collection even in a country like the Netherlands, but of course it certainly means that in the wider world there is a big bias in where our citizen scientists are likely to come from. And something I'll talk about next is that rich countries are typically data-rich countries, and we can get more into that. I've put a note here about self-driving cars. I think I'm going to call it a side topic for now. So self-driving cars is one AI intervention, and we can talk about whether or not it's good for the carbon footprint. We've spoken about that when we did the pros and cons in the last term. But it's something just to think about. So is that going to globalize? Is it going to have the impact that's expected? Does it require a certain infrastructure, like roads that are regular, that have a proper surface, cities that are well organized? Various limitations there. Just think about that one. I don't have a definite answer for it, and we're not going to talk any more about it. So data-rich and data-poor countries. One side of this is when we're deploying our solutions, right? So what we want is typically high-resolution data. And I think this comes in very clearly when we think about remote sensing. If we're doing geographic remote sensing, we have satellite data, we have plane data, we have drone data. I don't know if you've done this before, but if you go onto something like Google Maps and you look at the Netherlands, and then you take that and you look at poorer countries, you tend not to see the same quality of imagery, not the same resolution. Now, Google Maps is intended for consumer use. They buy or they create the imagery according to what their market is. But one thing that's really not obvious until you investigate it is that they don't have the same precision of imagery in every part of the world. And that's partly because there are richer people in certain parts of the world. So that's one obvious example that you can go and look at yourself. But it is also true for pretty much all the remote sensing data. So the Netherlands has a public source of remote sensing data gathered from airplanes. So the government basically pays for this to happen, so the whole country is scanned. Most countries don't do that, and certainly poorer countries can't afford to do that. So we have access to a certain sort of imagery that a lot of people don't. Now, satellite data, I think this becomes kind of interesting because there are many satellites which cover the whole planet. And NASA is perhaps the obvious example of an institution that covers the whole planet with satellite data, and they publish some of it completely public domain. So in that case, there is a kind of trickle-down effect that they are providing a public service for the planet. This is a good thing, and we should keep in mind what we can do with this data, because it's great that there are data sets that cover the whole planet. Of course, they are lower resolution and often less frequently sampled than some of the more expensive data sources. This plot, I saw this plot last week, and I think it's kind of, the difference is kind of astonishing. This is just weather stations. So if you think about where you get your weather forecast from, they come from weather stations scattered around the country. And it turns out that Europe has the highest density of weather stations out of all the continents. We just have loads of weather stations, and they're all, for any particular area, we use the nearest weather stations to help us estimate what the weather is and what the weather will be. And now look at when we get to South America and Africa, they both have very low density of weather stations. So if we want to model what their weather is going to be like, we simply have less data. And of course that's true for deploying, but it's also true for training. This makes a difference to deploying and to training. But apart from that, as we said, data sets collected in the rich world only will have, typically will have less good performance in poorer areas. And from lecture 2, we had this example. This is about the jay, the jay, and the most highly sampled bird in the data set was this one. It's the American blue jay, and that is not the most common jay. So actually, very well-known data sets, such as ImageNet, they have this bias across the rich world versus the poor world. And this is something that I produced myself. It's very simple to go into GBIF and say, show me all of the insect observations. And over here on the map, we see a kind of density map. And it turns out that Europe has all the insects. Does that seem likely? No, it's not very likely. So the sampling here, and this is all of the insects reported in the past 20 years, so since the year 2000. And yeah, this is clearly not evenly sampled. So Africa is very low in sampling. It turns out the Russian steppe is, or maybe there aren't many insects there, but the density there just doesn't reflect the reality. So how can we make... Oh, there's a question.
About the previous slide. Yeah, I was wondering about the density of weather stations, because I was thinking in my mind, okay, maybe it's because Africa has a lower population density, but then the
Yes.
second one is Oceania, which has an even lower population density. So,
Yeah.
what's the need to speak for a weather station? And why are they not? Does it really increase the accuracy of the weather that much? Or?
It's a great question. There are a lot of different factors in this, to be honest, and I can't give an answer that really sort of divides it all up neatly, but there are lots of different things going on. So, of course, the density of weather stations probably relates to the density of population, because it's the people that need the information. That's fairly clear. I think one thing that definitely happens for Europe is simply the fact that Europe is divided into countries that are pretty much self-governing. So they create their own weather system networks, right? So the fact that Europe is divided into countries is probably part of the effect here. The relative wealth is the obvious thing as well, but then, yeah, Oceania has a fairly low density overall. Maybe it's their relative wealth that means that they have this. There are also geographic effects. So across a big, wide, flat area of territory, the weather doesn't vary that much. Whereas if you have varying landscapes and varying sort of profiles of the landscape, then you might need a denser set of weather stations to actually get a good estimate of what the weather's going to be like. So even if we were sampling things perfectly, to get the best estimate of the weather at any point on the planet, we wouldn't go for a perfectly uniform solution. We might go for something that has specifically concentration around where the coasts are and the mountains are to get specific measurements. It could be that in Oceania they're concerned about hurricanes, and that's why they have more weather stations than you expect. So there's a lot in there. So how to make solutions global? Using the tech that is available is always a good starting point. So I take it as a lesson that smartphones are pretty widespread. We might assume that in poorer countries that mobile phones simply aren't used, but actually it can be that mobile phones are much more widespread than other types of computer. So smartphones can be widespread, but typically not very reliable broadband internet. And of course, available tech also includes the satellites that I referred to that are just giving us data about the world. Publishing open data can be a good way to make solutions global, and there are a few reasons that I'm saying that. So this example of NASA or EU just publishing remote sensing data, this is a good thing. It means that in various parts of the world, you don't need a big investment to get hold of this data because it's been made public. Crowdsourcing, so the solar panels example that we went through, that's based on crowdsourcing, and the data there are open sourced. Of course, that has the limitations of crowdsourcing. Species observations in GBIF. Now, on this final point here, we want to publish the outputs of machine learning, such as land use estimates. One way that we might think about machine learning is if I'm going to develop a system, I'm going to train an algorithm, and let's say the algorithm works really well, my next step might be to sort of hand the algorithm over to people. I can put the algorithm on GitHub, I can do whatever I like, people can use it, job done. Part of the problem with that is that if it takes cost and tech investment for other people to use that algorithm, there's still a barrier. But instead of publishing the algorithm, I could publish my estimated land use for the whole planet, and that's easier to use because now our future users, they don't have to run an algorithm themselves, they just have to grab some data that you've downloaded. There are plenty of examples of this, such as land use estimates which come from NASA and EU. They have run some algorithms. They don't just have the raw data. They have run some algorithms and they publish the results. Another example that comes to mind is that Google Alpha's recent work on protein folding, right? So they did this AlphaZero algorithm to predict protein shapes. And they haven't just published the algorithm, they've published a big sort of directory of the protein shapes that they've inferred. So that means that people don't need to run an algorithm, they just sort of look something up in the dictionary that's been published. Of course, collaboration is important, and collaborating to improve data sets. So it's not always easy from somewhere in the middle of a richer part of the world to collaborate with people far away, but collaborating to improve data sets, to fill in gaps is always important, and working directly with the users and the stakeholders. Of course, this last point helps to make the solutions global. It helps you to avoid falling into many of these traps. Now, the final thing I want to talk about is nature-based solutions, and this is an idea that is often worth thinking about, and we have to think about it specifically if we're thinking about very sort of tech-centric innovations. The phrase nature-based solutions comes primarily from the world of climate, and the idea is that it's about using natural features and processes to tackle social environmental issues, such as climate change. So if I take at the bottom there, we can say we're considering planting trees as opposed to CO2 removal from the atmosphere by technology, right? It's basically the same goal. We want to take CO2 out of the atmosphere, but we either do it using technology or we do it using an existing natural approach. Nature-based solutions are advocated for, and they're advocated for many reasons. It's not... Okay, this is not just like a pure hippie thing of we don't like technology, but there are many things that we've thought about already this morning which sort of relate to it. With planting trees, we know what the side effects might be. We know about the relative impact and usefulness of trees because we have a lot of experience with these things. Whereas with new untested technology, there might be side effects, there might be rebound effects. And so part of the motivation for nature-based solutions is just that we have higher confidence in their impact and higher confidence that they're not going to cause bad side effects. And they can have lower environmental cost to implement, and they can often have positive side effects. So we might be planting trees to soak up carbon dioxide, but the positive side effect might be that planting trees creates new ecosystems, creates refuges for wildlife, and so forth. So, within the climate world especially, the idea of nature-based solutions is popular. So, can we think of AI and nature-based solutions? I've said a few different times that AI is not the solution to these big crises, but AI can help to monitor and implement these solutions. And for me, that's kind of the core of it, right? We're not... if we think about nature-based solutions, we're not just giving up on all the tech. There are various ways that we can support nature-based solutions. Forest management, rewilding. Of course, remote sensing is one of the core ways that we can actually keep track of forests and related And in the biologging lecture last week, we talked a lot about understanding animal behavior and animal populations. And one of the things that we can do with that, even if we're just tagging a few animals to understand their behavior, we can understand what they do within animal societies and how to make sure that reintroductions of wildlife go successfully. Yeah, I'm going to leave that as an exercise for you to think about other examples. Many of the things involved in remote sensing, I think, could count as nature-based solutions. Okay, now for the very final chapter of the lecture today, I want to show you an example that involves some actual AI to do something which is a bit like, well, I'm going to consider it a nature-based solution and see if you agree. It involves reinforcement learning. Now, I think earlier in the course you said you were familiar with reinforcement learning, right? Can someone tell me what reinforcement learning is?
It's basically using rewards to help a robot or a machine achieve a certain behavior.
Yeah, good. Using rewards to help a machine achieve a certain behavior. And so, yeah, many of the examples that you see of reinforcement learning involve robots learning to take actions, or learning to play computer games, various things like this. And I think I was kind of surprised when I came across this, because it never really occurred to me to think, well, can we use reinforcement learning to not just to move a robot about, but to manage an ecosystem. So, yeah, here I've written that reinforcement learning, we're using machine learning to decide which actions to take. Your definition was more complete, though. Thank you. So here's the thing. This comes from a research paper last year by Daniel Silvestro, and I think it's super interesting. It's using reinforcement learning to decide which areas of land to protect. So we all know that there are protected areas, right? There are nature reserves where you're not allowed to walk or not allowed to walk your dog, various things like this. So what do we have on the screen? Let's have a simulated system. So this is looking down from above on an area of land. And in this example, there is a protected... Well, actually, yeah, there's a protected area down in the lower left here. And what you see on the heat map there is the amount of disturbance by humans. So where the protected area is, there are fewer humans, and so we have a lower amount of disturbance. This map is now divided into this grid of possible protected areas. Okay, so now what they do is they take a lot of information in. So in part B, we can see here there's a lot of information going in, such as monitoring the amount of anthropogenic disturbance, monitoring the species, monitoring climate variables, various other things that go in there. So when we're monitoring animal populations, of course, we want to know which species are where, but there's also other factors, such as the climate, the land use. All of these things go in as input data. So thinking simply, we can imagine this as like many of the machine learning topics that we've looked at so far. We're going to take these sort of remote sensing type map grids. You can think of it as piling a load of different sources of information up as input channels to a network. So then we put that into the deep neural network, as you see down here. It does basically convolutional and densely connected layers. So the actual network architecture is pretty much like anything you would see for image deep learning, except that the output, okay, we're using softmax, that's pretty standard, but the output is not a classification decision, it's a policy decision about what step to take next. And the step to take next could be, okay, this protected area, let's imagine, for example, that the policy isn't having a strong effect, so that it might be to get rid of this protected area. It might be to expand the protected area. And the reward that the system needs to learn is, it's the expected, well, let's say the expected species richness, so the expected number of species within this region. So this is the only paper that I've seen that's done this. I think it's really clever because this could then use reinforcement learning basically to tell anyone managing a natural habitat, it could tell governments, sort of an optimized way to protect certain areas or to change the management policies to maximize the benefit for nature. Here's their example of a simulated example of it applied to data from Madagascar. So here we see the whole island of Madagascar. They're comparing two different methods here. So what you can see is that the highlighted parts here are the bits that are important to preserve. So having run the algorithm through a lot of simulations, on average they find this quite detailed map of which bits of nature they decide to protect. And the simulated outcome is that you get a very strong, a much stronger protection of the number of species that are still there at the end of the simulation. I think that's that, yeah. Any questions about that? I don't, bless you, I don't have anything, I don't have any more examples. This is the only example, but makes sense? I think this is kind of cool because it's entirely compatible with very nature-based solutions. Here the algorithm is not in the habitat, it's just helping to make management decisions. Okay. So now concluding, with tech solutions, the route to impact is complex. We've seen a lot of negatives in this lecture, but all is not lost. We've seen that many solutions, some of them are more robust to these issues than others, and that applies to a lot of the things that we've talked about in the course so far. So remote sensing can be good in various ways. Citizen science can be good in various other ways, and almost everything that we've considered has something negative and something positive in the terms that we've discussed today. Some lessons, just general lessons to take away. Consider whether your machine learning will really generalize. Now, everyone kind of does that, but once you get sort of into your own project, maybe you sort of focus on the data set performance, and it becomes harder to really reflect on whether the system will really generalize in practice. Beware of assumptions about behavior, in particular user behavior. And so this second point about user behavior, this makes a big difference whether you have an intervention that relies on behavior change versus an intervention that doesn't rely on behavior change. So these are two of the big categories that we might consider in climate, for example. And of course, be conscious of side effects and feedbacks. And the best way to do that is to work with stakeholders and the people that might be bearing the costs of these things. Okay. So that's it. Let's see. This is the summary of what we've talked about side effects, and the longest part is about factors limiting impact. Global solutions, here's a list of kind of the main topics, but there are quite a lot of different topics, in particular the use of people power, and finally nature-based solutions.